Right, welcome to lesson 3 of the reaction rates topic. The title for this lesson is Following the Course of a Reaction Over Time, so you can write down that title here in blue. You don't need to write down what's written in red. So the lesson's about following the course of a reaction over time. What we're going to do is we're going to look at two different methods for doing this. We're going to look at collecting a gas and measuring mass lost, and I'm going to show you how to draw a diagram for both of those reactions. And then we're also going to look at the graphs produced when we follow the course of a reaction over time, and there's a few different things you need to understand about these graphs. So what I'm going to do this lesson is I'm going to use Scholar to talk you through this section. I'm going to also give you your Scholar passwords this week, and we'll definitely be using Scholar quite a lot in chemistry this year, but for this lesson I'm just going to show you how to use Scholar and talk you through the lesson, and everything that you need to take down in your notes I'll actually do on the whiteboard, but I'm just going to show you how to use Scholar. So I'll send you the link. It's scholar.hw.ac.uk. It's a website run by Heriot-Watt University, and it's got courses for lots of your different school qualifications. So you might be already using Scholar in some of your other subjects. So when you get to the Scholar homepage, you just click login. When I send you an email, I'll send you your username and password, so you should manage to log in fine. When you get logged into Scholar, you'll come to your homepage, and then you'll see all the different courses you're enrolled in. So I'm just enrolled in chemistry as a teacher, but you'll be enrolled in probably all of your different National 5s. I think they've got most courses on there, not everything though, not everything. So when you get onto Scholar, you want to click on National 5 Chemistry. Right, and once you get onto the National 5 Chemistry page, what you'll see is the 3 different units of National 5. So we're starting on the first unit, Chemical Changes in Structure. So if you click on that, you'll then see all of the different topics in the Chemical Changes in Structure unit, and then you can click on Rates of Reaction, or whatever topic it is that you're working on. Okay, and once you get to rates of reaction, you'll see that there's a few little sections within the rates of reaction topic. I'm just going to go straight to the bit on progressive chemical reactions because that's what I'm wanting to teach you today. But you'll see you should recognise a lot of this other stuff. So if you want to, when you get your Scholar login, you can go in and test yourself on all the rest of this. It's really good for revision and consolidation. So you've got prior knowledge, you've got a bit about collision theory and the factors affecting rate of reaction. So we've already covered that. So I'm just going to go straight to progressive chemical reactions. That really means the same thing as following the course of a chemical reaction. And the first one we're going to look at is measuring the change in volume of a gas. Okay, so from our previous lesson, we already said, this bit at the top, we said that reactions in which gases are given off are easy to follow because we can observe the change in volume as the gas is released. First of all, what we're going to do is we're going to draw 2 diagrams of different experimental methods to collect a gas produced during a chemical reaction. We're going to look at collecting a gas by displacement of water, and we're going to look at collecting a gas using a gas syringe. And like I say, the first thing we'll do is draw a diagram for each. If you tried my little home experiment, you will see that, if you don't have any of this equipment, one way to trap the gas produced is perhaps to use washing up liquid. That's not a particularly accurate or great way to do it though. So both of these methods are more accurate than what we did in that home experiment. So first one, so what to do is you're going to write down method 1, collecting a gas, and then we'll draw the 2 diagrams. So the first one is going to be displacement of water, and the second one is going to be using a gas syringe. Now, we're going to draw the diagrams in a very similar way to what's on the screen here, but not in exactly the same way. So we'll start with displacement of water. And what we've got here is we've got our reaction being carried out in a conical flask. We've then got a stopper in this conical flask, but coming through this stopper is what we would call a delivery tube, and the delivery tube can carry the gas through into this basin of water, and in the basin of water we've got a measuring cylinder that's been completely filled with water and turned upside down. So that's what this thing is here, and what we do is we make sure we put the delivery tube right under the opening of the measuring cylinder so that when the reaction starts, the gas can bubble through and we can collect the gas in the measuring cylinder like so. So how do we draw this diagram? It's very similar to this, But the main thing that we have to do when we're drawing this diagram is we have to make sure that we don't have any blocks in the delivery tube. So here we've got the delivery tube's it looks like it's almost blocked by the stopper. When we draw a diagram for this of this for the SQA, what we have to imagine is that we've taken a cross section that we've sliced right through the stopper and right through the conical flask, and we're going to draw a cross section. So we're going to draw it as if you can see that the path is clear for the gas to travel right through this apparatus. So how to draw that then? I think the best way to do it is to start by drawing the conical flask, and you'd want to use a ruler at least for the main long lines on the conical flask. So I would draw the conical flask first, and then I would draw your delivery tube, and that just helps you to make sure you don't do any lines across your delivery tube. So you're going to start the delivery tube around the bottom of the neck of the conical flask. You're going to go up, across, down, and around like this. And then when you draw your next line, be really careful that the two lines don't touch. You want to leave a space between the lines because you want there to be a clear path for the gas to travel. Once we've done it like this, then I think it's nice and easy to draw in the rest of the diagram without accidentally drawing any lines across the delivery tube. So you can add in your stopper. That's quite important because what we want is we want the gas to go through the delivery tube. We don't want it to just escape into the air. You can also draw a little line because usually what we have when we do this reaction is we have an acid typically in here, and then we react the acid with something that's going to then produce a gas. So then we can add in the water bath. Make that a bit taller. And we can add in the measuring cylinder. Now, when you're adding in the measuring cylinder, make sure it clearly goes right over the where you've got the delivery tube in, and also make sure, this might sound like a silly little point, when you're drawing a measuring cylinder, make sure you put the little lines in. That just makes it clear that that's something that can actually measure the gas produced. The other thing you could do would just be to label it, and we'll label the whole diagram anyway. And then you're going to add in your water, so you can just draw a little line going across here. But again, see how I've taken care not to draw my line through the middle of this delivery tube here. So the delivery tube has to be clear. So we'll just label that quickly. So you've got your conical flask. You've got your measuring cylinder. And you've got a water bath. And finally, if I can squeeze it in here, delivery tube. Okay, so I'd like to see this diagram in your notes under the title Method 1, Collecting a Gas, and this is collecting a gas over water. So what this allows us to do is to trap the gas and measure how much gas is produced over time as this reaction takes place. So that's what we mean by following the course of a reaction over time. We're measuring how much product is produced over time. So this method of collecting a gas works pretty nicely. It's probably the cheaper one because measuring cylinders, all the equipment here is nice and cheap. The one problem with this method is that it would not work if you have a gas that dissolves in water. So some gases do dissolve in water, and if you have a gas that dissolves in water, then this method is not going to be suitable. And that's one of the main reasons why we would use the next diagram, the next method that I'm going to show you, which is using a gas syringe. Another slight problem with this is that it can be kind of a little bit difficult to read the scale on the measuring cylinder because the measuring cylinder is upside down. So that's another reason why the gas syringe can be kind of helpful. Okay, so make sure you've got the title and this diagram and the labels and everything copied in. And we'll then look at the next one. So the next method for collecting a gas is collecting a gas by gas syringe. So gas syringes are good, but they are a little bit more of an expensive piece of equipment. So as we release the gas, the plunger for the syringe will just move backwards according to the volume of gas that's been produced. So that's quite a nice method. And again, what we're going to do is we're going to draw a diagram of that one. And again, it's very similar to the diagram that's on Scholar here, but we're just going to draw it in such a way that we make sure there's nothing blocking this tube that's going from the conical flask to the syringe. So I'll just rub out the diagram that I've got down here and then draw the next one for you to copy down. Right, so I've just sketched that diagram in the same way, drawing the conical flask first, then the delivery tube, and then the rest of the equipment. Now, when you're drawing this particular diagram, one thing that's important is again to make sure that there's a clear path for the gas to travel from the conical flask. I'll just draw my liquid in there again, from the conical flask into the gas syringe, so you don't want any lines blocking off this delivery tube. And the other thing to make sure that you do is to draw these little measurement lines on the gas syringe as well. It might sound really silly to me, it's a little bit silly, but I've been told that you might lose a mark in an exam if you don't put the lines in, if you're asked to show a method through which you can measure a gas. Now, gas syringes, like I discussed, work best if you've got gases that are soluble in water. And to be honest, if you're asked in an exam to draw a method to collect a gas, this is the best one to draw because this one works for all gases, whereas the one before with water only works if the gas is insoluble in water. So this is the one to go to if you're asked to draw a diagram for collecting a gas. So I've obviously had to rub out my other diagram, but you should have two diagrams drawn in your notes now, and you should have this written down. So gas syringe is best for gases that are soluble in water. So we're now going to have a little look at what this actually looks like when we follow. Right, my previous video got cut off, but we're just going to pick up where we left off. So in the previous video, what we had looked at is we had looked at two different experimental methods which we could use to follow the course of a reaction or measure the progress of a reaction over time. And what we're going to look at in this video is what the shape of a graph produced from these experiments actually looks like and what actually happens in these experiments. So again, I'm using Scholar and I'm just going to play this demonstration here. So what I want you to pay attention to is the speed at which the gas is given off at the beginning of the reaction and then as the reaction proceeds. So when we start this experiment, hopefully what you can see is, I would say the gas is being given off pretty quickly at the beginning of this experiment. We've filled the measuring cylinder up quite a lot, quite quickly, but then as the reaction proceeds, we can see that the rate of bubbling, the rate at which the gas is produced, is slowing down over time. And that's what's being shown on this graph. So at time equals 0, we had 0 centimetres cubed of gas collected. In the first 5 seconds at the beginning of the reaction, the gas was produced quite quickly, and already in the first 5 seconds we've got about 7 centimetres cubed of gas produced. And then as the time proceeds, the increment, the next amount of gas produced is slightly less. So we had 7 produced in the first 5 minutes, but then in the first 5 seconds, then in the next 5 seconds, we can see that the line doesn't go up as much as it did in the first 5 seconds. And then again, as time goes on, the amount of gas produced in the next 5 seconds, each time it decreases a little bit. So the reaction, you can see that most clearly from the bubbling, but what you need to know from this about this graph is that this is showing that the reaction speed is decreasing over time. And then eventually we reach a point where the reaction is finished. We've collected the final volume of gas. So the total volume of gas collected in this experiment, I think, looks like it's about 13 centimetres cubed, and no more gas is produced at the point that the reaction is finished. So we can see here that the reaction, after 25 seconds, the line just goes completely horizontal and no more gas is produced. We're going to take a note of that in a little minute once we've looked at the graph from the second experiment. So, the second experiment was measuring the mass lost over time. Okay, so in this case, we're going to produce a graph which looks kind of similar, but also a little bit different to the one before. This time we're measuring the mass lost in the reaction. So you can see from the balance here that the total mass of the apparatus, that just means all the equipment here, is 260 grams at the start. So at time equals 0, now they should really have a 0 on this graph. We'll make sure we put 0 on ours when we do a sketch. At time equals 0, the mass is going to be 260. Now, what I'd like you to do is think about what's going to happen to the mass over time of the apparatus as the reaction proceeds. Well, hopefully you remember that when a gas is given off, the mass of the apparatus is going to decrease because the gas is just escaping into the air. So let's see how that happens now. Okay, so you can see at the start of the reaction, we've got lots and lots of bubbles. The gas is escaping quite quickly. So the mass lost in the first 5 seconds is quite a lot. But then as the reaction proceeds, the reaction is slowing down a little bit. And so each time we measure the mass lost, the increase is getting slightly less. So the increase in mass lost is getting slightly less as we go down. And then we get a curve that's quite similar to what we had before. So it's very steep at the beginning of the reaction, and then it gets a bit shallower, and then finally it flattens out at the end of the reaction. So what we're going to do is we're going to sketch a little sketch of both of these different graphs, and then we're going to take some notes to explain these graphs. It's a common type of question that comes up. It's really important that you're able to understand what's going on and explain what's going on in these graphs. So I've done a little sketch for you here already, so you might want to pause the video now and copy down my axes. So we're going to draw them side by side, or you can, if you can't squeeze them in side by side, you could do them one below the other. We've got the gas produced method, so remember you can either collect that over water or you can use a gas syringe to measure the volume of gas produced. So then you've got the volume of gas on the y-axis, and we're going to measure that over time, so time's on the x-axis. And then the other one that we looked at was measuring the mass loss in the reaction, and this time we're going to measure the mass of the apparatus in grams over time, so time again is on the x-axis. So if you want to pause the video, you can do that and write down these axes, because what I'm going to do now is just do a rough sketch of the shape of the line that you would expect. So when we're measuring the amount of gas produced, or the volume of gas produced, what we will get is we'll get quite a steep increase, quite a quick increase in the volume of gas in the first few seconds of the reaction, and then gradually that increase is going to level off. So we get a shape a bit like this. And then similarly, well, not similarly, it's a kind of similar shape, but almost like the opposite. When we are measuring mass loss, we're going to start with quite a high mass, because we're just measuring the total mass of our apparatus. That'll just depend on what our equipment is. And the mass is going to drop quite steeply, quite quickly in the first few seconds, but then that drop is going to level off. And then at a certain point, the line will flatten out, and that tells us that the reaction is finished. So make sure you've got these two graphs written down, and then what we're going to do is we're going to actually just copy down some notes from Scholar. Okay, so this time I don't think I'm going to write this out. I'd like you just to copy these notes from Scholar. So we're going to take a note on how we can interpret these graphs down here that we've just drawn. So rate graphs can be interpreted in two different parts. First of all, we can use them to have a little look at the rate. And what I'd like you to write down is that the gradient or steepness of a graph tells us about the rate of a chemical reaction. So the steeper the gradient, the faster the rate of reaction. What you can imagine is if this was a hill, a picture of a hill, this is the steepest part, this is going to be the hardest bit to walk up. Now, the thing to pay attention to is that the steepest gradient is at the start of the reaction. The gradient decreases, the slope decreases as the reaction slows, so it's less steep, and then when the reaction has stopped, the line flattens out, so the gradient becomes 0. I'd also like you to copy down this explanation. So the explanation says, generally, the rate of reaction will slow as it progresses because the reactants are being used up. So that's why we get this shape. You can link this back to the effect of concentration on reaction rate. So at the very beginning of the reaction, the concentration of, say, your acid that you're using is going to be at its maximum. But as the acid gets used up, the concentration of that acid is going to decrease. And as we know from our previous lessons, as the concentration of a reactant decreases, the rate will also decrease. So that's why generally the rate of reaction will slow as it progresses, because the reactants are being used up. And then we can see that the gradient of the rate graph starts steepest, then slows down before becoming straight, and that's when the reaction has finished. But the key idea is that this that we get a slowdown in the rate because the reactants are being used up. So I want you to copy down all of these sentences underneath where you've drawn these graphs here. If you want to, you could re-sketch the graph, but you don't need to because you've just drawn the graphs in your notes here. Okay, and then the other thing that we can tell from these graphs here is that we can see the end point. We can get a time for the end point of that reaction. So when the line graph becomes horizontal, that is called the end point. And this tells you, the horizontal line tells you the total volume of gas produced in this example, or it could tell you the total mass lost. So if you wanted to find the end point of a reaction, you would find the very start of the point where the graph becomes horizontal and then follow that down to the time axis. So what I'll actually do is I'm just going to write down what I think you should have got from these from these notes, and then I'm going to just draw a couple more lines on the graphs that we've just drawn just to explain them. So just to summarise, what you should have written down is the steeper the line, the faster the rate, or something along those lines. The rate slows down over time as the reactants get used up, and when the line starts to become horizontal, the reaction has finished. So all we're going to do now is just add on a little marker on our two graphs that we drew to indicate when the reaction finished. So this first one here, you're looking for the very point, the point at which it just starts to become horizontal. So here I think it's still sloping up a little bit, say possibly about there it becomes completely horizontal. It'll be obvious when you've actually got graph paper, you should be able to get that a bit more exact. And to find the time then at which the reactant stops, you just follow that down to the time axis, to the x-axis. So you can just add in a little note to tell yourself reaction stops here. There we go. So the reaction stops at that point, at the point at which it starts to become, the line starts to become horizontal. And then the next one, the mass of apparatus, again, you're just looking for the point at which the line first starts to become perfectly horizontal. So here it's still just going down just ever so slightly. I would say about there, just at about 20 seconds is where the reaction stops. And of course, once the reaction has stopped, there won't be any further decrease in mass because no more gas is given off. Similarly, there won't be any further increase in volume of gas because the gas has stopped being produced. Now, the last little bit that we're going to look at is how the total volume of gas produced is determined. So it's to do with the amount of reactants. Obviously, the more reactants we use, the more gas we're going to get. But slightly more complicated than that. What we're going to learn about is something called the reactant in excess and the limiting reactant, and that will be the last part of this note. Okay, so how do we know how much product will be produced in a chemical reaction? Well, in most chemical reactions, we have two reactants coming together. One of these reactants will be what we call the reactant in excess, and that reactant is not used up. The other reactant will be what we call the limiting reactant, and the limiting reactant is the reactant that does get used up. So in any chemical reaction, the reactants usually combine in a particular ratio. What that means is, unless we have that exact ratio, we're usually going to have more of one reactant than we actually need for the reaction to happen. So we're going to have a reactant that's in excess, which means we've got more of it than we can possibly use to react with the limiting reactant, and the limiting reactant will be used up. A little example of this would be if you were burning like a log in a fire. when you're burning something in air, the oxygen is greatly in excess. So you're never going to use up all of the oxygen in the air if you are just lighting a small fire. So the oxygen is in excess, and like I say, it's never going to get used up. Whereas the log or whatever you're burning, that would be the limiting reactant, and that's the thing that's going to get used up. You're going to run out of fuel before you run out of oxygen in the air. What we need to know, and how this relates to these kind of graphs, is the amount, so the mass or concentration of the limiting reactant controls the total amount of product produced. So if you think about it, you know that burning a fuel, most fuels that we use, burning a fuel produces carbon dioxide. The amount of carbon dioxide produced is going to be dependent on the amount of fuel or the amount of wood used, rather than on the amount of oxygen that we have in the air, because the fuel is the